Hello, today we will be exploring how to implement a co-combustor, a co-fluidized bed reactor in Rocky and Fluent. So it's a coupled CFD-DEM simulation. So basically I have this fairly simple configuration here, a rectangular fluidized bed with a structured uniform grid mesh developed in Ansys workbench meshing. So we basically all we have is an inlet with air with some water as well, and an outlet. And basically, it's a single species. Sorry, a single mixture um, with several species being added at the bottom with a velocity inlet and basically exiting from the top. I'm using the x coordinate as my vertical axis here. So basically, the air will interact with the particles from Rocky, and it will induce combustion of the particles. So the particles will get oxidized by oxygen, um, generating CO2 and CO as well. And there's also reactions that are enabled in the gas phase with CO and H2O as well. So basically this is the simple setup. It's a relatively coarse mesh so that the particles are and like the particles we need to make sure that the particles are smaller than the mesh itself, each cell element. So basically I can provide the size of the mesh, so 11,250 elements, and basically we can do a mesh check as well to see the total volume. So it's a fairly small segment of a fluidized bed, just for demonstration purposes. So basically when we look in the model, we have species transport enabled, and with species transport we have reactions, volumetric reactions enabled, with finite rate enabled, no TCI. So basically using the simple settings here, we could make it more complex for sure, but this is just for demonstration purposes. So for the materials, the mixture, we have a number of species added. So we have H2O, O2, H2, CO, CO2, and N2, and the nitrogen, which is the last species, and it has to be set as the last species for the coupling to work properly. Yeah, and basically for reaction rates, we have two reactions, CO and H2O forming CO2 and H2, and another reaction is CO and getting oxidized by oxygen and forming CO2. So that is basically it. The density is set to ideal gas. Yeah, there's not much to it. So basically the default settings for basically air are used here. So once we start running the simulation, what will happen is air is going to be added through the inlet boundary condition, which is a velocity inlet, and we are using a velocity magnitude of 0.7 meters per second, and air is set at a temperature of 300 Kelvin. So we don't really need to hit the air that comes in. I did add, I did patch the domain at initial time to make sure that the temperature was high enough to induce ignition, and we are adding basically 20% oxygen by mass, 10% water, and we also have the balance being nitrogen, so 70%. The value of your velocity magnitude will dictate basically how the particles are going to get fluidized. So the dynamics, the motion of the particles will be determined by how strong your velocity magnitude here is, or your mass flow rate of air is. So a very high velocity would actually induce a lot of fluidization, or because your particles are relatively light, they can be carried all the way to the top, depending on if you use a very high value. So basically, for walls I'm using adiabatic with non-slip boundary conditions, and outlets is just a pressure outlet. So that's all we really need to do on the Fluent side, and then once we've set everything up, we can go into the basically the Rocky side. But I did create some contour plots just to visualize. So for now, because we're at time 0, we do not have any reaction happening yet, because the reaction will depend on the presence of the particles. The time step I chose was 0.02, and basically Rocky will report every 2 time steps, so every 0.04, and I'll show those details. So basically that's all. Once the simulation is set up, you can save the case file. I would also do some initialization on my own side. So basically for initialization, you press initialize using the standard method, and I did patch for temperature, basically temperature at 1000 Kelvin at time 0, and I also added some water in O2 as well at time 0 to help start combustion right away as soon as the particles are added into the domain from Rocky. So that's it from the Fluent side. Let's move to the Rocky side. Okay, so moving to the Rocky setup. So the first thing is we have to define our study. Here you can label the name. So you can call combustion fluidized bed, and I can add some description as well. Basically, and then we can move to the modules. So the modules that we're using are fairly simple, so contact, overlap, monitor, and I also added a CFD coupled particle combustion beta module. So that's basically it. So if you look here on the CFD coupled particle combustion module, we have different properties for oxygen, CO2, and CO. The O2 laminar diffusivity, so the formation enthalpy as well. So basically we can set these up. So I used the default values for laminar diffusivity for oxygen, CO2, and CO. And for reactions, we have 2 reactions, R1 and R2. So R1 is carbon reacting with oxygen, forming CO2. And reaction 2 is carbon reacting with CO2, forming 2 molecules of carbon monoxide. And basically it's an Arrhenius rate for each of them, for each reaction, so where we have a pre-exponential factor. And we also have an activation temperature. Sometimes we write that in terms of activation energy, or sometimes we can write that in terms of activation temperature. So we can convert from one to another if you have values in terms of activation energy. So, but I basically used the default values, and you can see that the activation temperature here for the reaction one is lower than the activation temperature for R2, indicating that likely this reaction can happen at a lower temperature than the second reaction. The second reaction requires the presence of CO2 for it to occur, um, and yeah, the energy barrier seems to be higher based on the activation temperature. For physics, we need to define the gravity, basically gravity pointing in the negative x direction. As you can see from the geometry here, air will be basically moving from the inlet boundary at the bottom uh, to the top, and yeah, nothing to change here in momentum. And for thermal, you can just click enable thermal, and of course graining enabled. So that's basically it for physics. Now moving over to materials, we have to set up a material, a default material. So here I'm using fairly simple density values, 1200 kilograms per meter cubed, with a predetermined Young modulus, thermoconductivity, and specific heat, and so on. So these values can be played around, or can be modified depending on if you have a more specific material or a specific type of code that you want to evaluate within Rocky. You can modify these values. And we do not have any fluid defined in Rocky, so we don't have to worry about it. So for geometries, we first of all have to import geometries. So I've already done that. So we can import wall and basically read the case file, the Fluent case file that we have, and it will generate the geometry here. And basically everything is defined as a wall. Here I do not have any surfaces, so a surface would allow me to add particles or extract particles as an outlet. But here I'm treating everything as a surface for the particles, and the way I'm adding particles is with a volumetric injection or inlet at time 0. For particles, now we have basically two particle sizes. We have particle 1, which is 3 millimeters in size, and we use the default particle material, and particle 2, likewise same material but bigger size, 4 millimeters. So we have two different particle sizes in our simulation, and this basically allows us to visualize. So I'm going to actually click this so we can visualize where the particles are. So this is how they are added into the simulation using a volumetric inlet, which I can go with right now. So basically I defined the bounds of this volumetric inlet to be within the box that's shown here. And basically I have half of the mass for particle 1, half of the mass for particle 2, and they're all initialized at 1000 Kelvin to facilitate ignition. And you define the region here. You could use the geometry, using the geometries to compute the bounds, basically, or you can manually pull these spheres in different directions so that it matches the geometry. So I roughly got the geometry manually here. I could have modified it slightly, but basically that allows me to set up a region within my domain where I want the particles to be initialized. And then once the simulation starts, this is gonna basically, the particles are gonna settle, but not quite, because they're still are already experiencing the flow of air coming from the bottom. Yeah, so this is an important part, the inlets and outlets, and then I don't want to. You saw that I was by accident tried to pull this, and it wanted to basically restart the simulation, so I said no, and I want to keep all the run that I have done already. But like moving over to the CFD coupling, which is a key part of this study, um, is first of all we have interactions between the particles and the gas. So this is where you specify them. So drag law and convective heat transfer law. So the convective heat transfer law is required when we're doing CFD coupling with basically combustion, which requires heat transfer between particle and the surrounding gas phase. So we do have to have something here, and we have basically Rand's Marshall and Whittaker and Gunn as well. So these are different options. So basically the same settings are used for both particles. For coupling, I said is volumetric diffusion, and for zones and interfaces, we basically select the cold, fluidized bed, regular solid. So this is actually from the Fluent case file. So this is where actually we have the we load the case file. So when we basically when we enable, so this module requires a two-way coupling between Fluent and Rocky. So I have to first of all enable CFD coupling. So here we can see disable CFD coupling, but before that we had enabled CFD coupling before I had enabled it. So once it's enabled, it will prompt you to select a case file, and this is the case file that I added. And we can use data initialization, so it uses the initialized data file that I generated in Fluent as my initial point, so with all the patches and everything. And I'm also keeping only two files basically, so that is basically it. And we do have to go back here and enable this region, the coupling fluid cell zone. And yeah, so basically once this is set up, we can start our run, and there's not much to it. So once we start our run, and I've already done that, you press start and it will basically run like an 8-second simulation, and I should have shown this as well. So a simulation duration of 8 seconds, we can extend that if we want to, with basically a Fluent output multiplier, so that we can get results every 0.04 seconds. And you can see the particles settling down in their position, and as we advance in time, you can visualize the particles interacting with the gas phase as well. And we can visualize that by basically going to a Fluent and making this visible, so you can see the vectors for the gas phase flow, colored by fluid velocity. And yeah, so you can see how basically the fluid is moving, and we can track with it the particles as well. So given that we have so many vectors, we can actually increase the stride, so we have a more easier visualization of the flow field through the domain. So you can see how the particles are affected by the flow, and the flow is also affected by the particles, by how the particles move. And the particles here are colored by their temperature, so I should go here into particles. So the nodes are colored by temperature, and we can color them by different variables as well. So if I basically select reaction rate, we can visualize where the reactions are more predominant. The reaction rate for C oxidation with O2 forming CO2. So you can see it's basically where we have a lot of like more interactions with the air flow, especially in the open regions or close to the bottom. We have a bit of reaction at the top as well, because it depends on the concentration of O2. So you can see in this hole that forms, we have quite a bit of reaction happening through this zone as well. So it depends a lot on the fluidization as well. So if we actually look at a time plot, um, you can see basically the rate of reaction 1, the average rate of reaction 1, how it changes with respect to the velocity of the particle. So as the particle velocity increases, there's a bit of a bump, or increase in the reaction rate for the first reaction. And once the particle reaction velocity decreases, once they settle down, and they kind of follow this cyclical pattern as we run the model, the reaction rate drops. We can also look at things like the basically the temperature of the particles over the course of the simulation using the time plots. So at time 0 they started at 1000 as I initialized them, and then they go up basically to close to 1100 Kelvin. And the green line here reflects the sum of the particle mass, so we can see that there is some consumption of the particle over the course of time, but it's not that much. It's pretty small percentage, because we basically haven't run this model for long enough to see a substantial decrease in temperature in the particle mass, which would likely result in an increase in the particle temperature and the gas phase temperature as well. We can also plot things like the particle size, the average particle size for combustion for basically for this model. We can see that they drop over time. The average size decreases. So yeah, so this is basically what we have here, and I can quickly play so that we can visualize, and I will change the back to temperature, so we can see that as we run this model, the particles are moving. Their color is slowly moving from a more blue and green color to a more yellow and red color, indicating that their temperature is going up. You can see the cyclical pattern as well. So they go up and then they go down, and then they go up again, and then they go down. So there's a fairly cyclical pattern that we see in the plots as well. So basically the air pushing the particles, fluidizing these particles, and then exiting once the upper layer of particles becomes small, and then we reset to time 0. So that is basically it. I also should note that I'm using a GPU solver for the DEM for Rocky. So basically this can be set up in general, and then I'm using a GPU solver for this model, and a CPU solver for Fluent. So basically once we start the simulation, what will happen is Rocky and Fluent are going to run at the same time. You're going to have a Fluent window popping up depending on what kind of argument you used for this two-way coupling, and then you're going to be able to see the Fluent results in its console. So that's basically it. Thank you so much and have a nice day.